Yes, today I'm going to talk to you about potential energy diagrams. So what is a potential energy diagram? This is a potential energy diagram. Here are two potential energy diagrams. And potential energy diagrams actually show the change in potential energy of a system as reactants convert to products. So that's to say that the energy change that occurs during a chemical reaction. So the energy is not the same for reactants and products. It happens to change during this entire chemical reaction. And there are really two kinds of potential energy diagrams. One's an endothermic and an exothermic. And both of them are very distinct from one another. So if we look at this picture right here, okay, so if you look at this picture right here, you've got two different energy diagrams. This is an exothermic and this is an endothermic energy diagram. Now if you look at this, let's pretend that you have a ball, and your ball is on top of this right here, this plateau, and you're rolling the ball, and you roll it, and then you come to this hill. Now you're going to be rolling your ball uphill, but then when you get on top of the hill, your ball is going to roll downhill. The slope, uphill slope, is not as great or as large as your downhill slope. That's the characteristics of an exothermic and a potential energy diagram. On the other hand, the endothermic, you have your ball again, and you're rolling your ball. You're going to roll it uphill. But notice that the slope to the uphill is a lot greater. Once you get to that top of the hill, then it's going to roll down. But that ball, that downhill slope is much smaller than the uphill slope. So characteristics of an endothermic reaction or endothermic energy diagram would be that you would have the uphill slope would be a lot greater than your downhill slope. And with that being said, you have certain characteristics in an energy diagram that you guys will be responsible for and what you need to be looking at when you're reading it. First of all, just to talk about graphs real quick, that this on the y-axis, this is called the reaction pathway. Okay, so this is the reaction pathway right here. This reaction pathway actually tells you the progression of the reaction. On the y-axis, on the other hand, you have the quantities or the measurement of the potential energy. And potential energy is measured in kilojoules. So this is true for both endothermic and exothermic energy potential energy diagrams. So some of the characteristics you need to be looking out for is right here where the reactants are. So let's say that you have a chemical reaction right here. Okay, this chemical reaction, you guys, let's say that you have the reactants right before the arrow on your left-hand side, and then on the right-hand side you have your products. Well, your reactant here on your diagram, and they are a certain distance away from the x-axis. This is where your reactant energy is. So you would simply, I've just made up some numbers to just give you an idea how to do the calculations, but it's really the energy of the reactant. It starts off at 60 kilojoules minus 0, so you're going to go all the way to the bottom, minus 0. So the total energy of the reactant energy is 60 kilojoules. The same thing would apply right here for B, which is the energy of the products, for the products. So you've got the products that start off at 20 kilojoules, all the way going down to 0, minus 0. So the overall energy of the product of the overall energy of the products is 20 kilojoules. The third and probably the next two characteristics of this energy diagram are the most important. The first one is right here. The third one that we're talking about is the activation energy. The symbol is really EA, standing for activation energy or energy activation. So this is where the bump is or the hill is. You always compare the energy diagram to where the reactants start. So it's the hill going all the way to where the reactants start. So what exactly is an activation energy? Activation energy goes back to something called collision theory. And it's basically collision energy. It says when all particles collide, a certain amount of energy is needed to progress the reaction. So when you have the reactants right here, some of these reactants will go through the entire reaction, become products. Some of the reactants don't, and nothing really happens with them. They never go through the entire reaction. In order to make sure that those reactants do go through the reaction, you need to, there is something called collision energy. So it's basically the activation energy is the energy needed to activate the reaction to allow those reactants to become products. So in this case, your activation energy goes all the way up to 100. So it would basically be 100 minus 60. And 100 minus 60, that would give you 40 kilojoules. So in other words, in order for this reaction to happen, the reactants need at least 40 kilojoules of energy to allow this reaction to go through and become products. Now, the last form of energy that you will be looking at is the change in enthalpy. Now, the change in enthalpy is, remember this change in H. Remember that this change in H is actually the change in energy flow. Because you've got your energy that's that's changing form and the flow of it, you can actually calculate that. And the change in energy flow is always the enthalpy of the product minus the enthalpy of the reactant. So it's really product minus the reactant. Once again, what you're going to do is you're going to compare the reactant to where the products are. But this time the product is starting off at 20. So it's going to be eventually, your enthalpy is going to be at 20. For your products, it's going to be at 20 minus 60 where your reactants are. So you can see that here, your product is 20 and your reactant goes all the way to 60. So it'd be 20 minus 60, which would give you a negative 40 kilojoules. Now, this negative 40 kilojoule means that this is the energy that is removed from the reaction. So, and really, this is all you need to know for a potential energy diagram. Just 4 different, in order to read it properly, you've got to be looking at 4 different aspects of it. The most important, I would say, is the activation energy and the change in enthalpy. That was for an exothermic reaction right here. Now, if you look at it, we do have an endothermic reaction, and it is very similar to your exothermic reaction. Once again, if we have an exothermic reaction right here, you've got your reactants that would be here, and then you would have your products that would be present right here. And these equations that I'm giving you are no way examples shown on these graphs right here. The numbers on the graphs I've just made up to give you a good scale to look at, an easy mathematical scale to look at. So once again, we're going to do the energy of reactants, and it's where the energy reactants start off. In this case, it is low energy of the reactants, so it's 20, going all the way to the x-axis, which is 0. So 20 minus 0 would give you 20 kilojoules. This is to say that in order for this reaction to go through, your reactants need to at least have 20 kilojoules of energy. And then, of course, your products here, your products have an energy of 60, and go all the way to 0. So this is to say that in order for your product, energy must be at least 60 kilojoules in order for any products to be produced. So those are the simple ones. But then let's look at the activation energy here. So you've got your hill. Your activation energy, remember, goes from the top of your hill all the way to your reactants. In this case, it goes from the top of your hill all the way to your reactant here. So if you're trying to calculate the activation energy, it would be 100 minus 20 would give you 80 kilojoules. That's to say that 80 kilojoules is the energy that is needed for this reaction to take place, for it to be activated, and for this reaction to occur. You need at least 80 kilojoules of it. Notice that this 80 kilojoules is quite high compared to the activation energy of an exothermic reaction, where you really had 40 kilojoules. And so you've got 40 kilojoules to 80 kilojoules. Clearly, this endothermic reaction takes a greater amount of activation energy for the reaction to go through. The last characteristics you want to look at in your energy diagram is your change in enthalpy. Now, the change in enthalpy, remember, goes from where the products ended to where your reactant started. So it is products minus your reactant. In this case, your products ended at 60 minus where your reactant is 20, and that gives you 40 kilojoules. Well, that's not a negative. That's a positive 40 kilojoules. So that positive sign means instead that the energy right here will be absorbed. Now, there are some differences between exothermic and an endothermic potential energy diagram. These two differences they're big differences that you really cannot ignore. And that is looking at the activation energy and the change in enthalpy. The activation energy in an endothermic reaction is much larger than the activation energy of an exothermic reaction. So what you can conclude by that is that at the beginning, you need more energy to allow the reaction to happen than an exothermic reaction. Another difference between the two diagrams is that the change in enthalpy is absorbing more energy in an endothermic reaction. So in an endothermic reaction, you're absorbing energy, but in an exothermic reaction, the change in enthalpy, you are actually releasing the energy. So that's a big difference, is that exothermic is all about releasing energy, and then your endothermic reaction is all about gaining energy or increasing it. So this was just a really quick lecture on potential energy diagrams and what they actually mean. Potential energy diagrams, you guys, are if you can learn how to read them correctly, they can give you a lot of information, and it is, it goes back to the original principles of thermochemistry.